I'm not sure, it's a mic just, can you hear me okay at the back? Right, great. So, thanks very much, Mike, for inviting me to this program. I've been having a great time already, and this is just a fantastic place to work. I haven't talked about this before, so it'll be slightly rusty, but this is sort of something that we've published one paper on and we're still thinking about and still very much working on, so hopefully you can give me some comments. This is one of the models we're going to be assessing later on. So I'm very much of the point of view that density estimation is a really good thing to do if you can. So no matter how complicated your problem is, it's interesting to think about trying to model the joint distribution over every single variable in your problem. Now that might be exceedingly hard, and maybe you don't actually need to do that to solve the problem you're interested in solving. But conceptually, if we could do that, then a lot of nice things would follow. We could answer any question we're interested in. And I think it's worth trying to attack, and it's worth trying to do that as well as we can, whenever we can. So the obvious question is, once we've got a generative model, if it's for a really difficult problem, we know it's not going to be perfect because we're never going to create a model that spits out beautiful images like we see in the real world or spits out real text. So we know that our joint distribution isn't going to be the real distribution that's in the world. So we need to be able to assess how well we're doing. How close are we to this unachievable ideal?
Can I ask, what do we think about as x?
Okay, so for this, it's going to be some vector, hundreds of dimensions. For most of this talk, it's actually going to be binary, 0, 1. But it could be anything you like. So typically, in the machine learning type of view that I live in, you would extract a load of features from the object you're interested in, which are often binary just because that's for robustness, but they could be real values, and then you model that vector.
You might have vectors of different length, or is that?
Yeah, you could do. I'm not going to get into that sort of detail. So for example, for an image, you just unravel it in a raster and it would be a vector of real numbers. Okay, so here's like the meta learning algorithm, that the most simple thing you could imagine. I've got some model, I want to know if it's good enough, and then if it's not, I will go around and look for other models. So this step 2 could be your favorite parameter fitting algorithm for your favorite model, and then I want to say, once you've done that, is that good enough or do I want to keep going?
So what's a model? Is that a probability density?
So a model here is a class of probability densities that could have some free parameters which you're going to fit or sum over if you're a Bayesian or whatever. So let's have an example of the list of models then. So you could start off with the simplest possible things you can imagine, like you could just fit some single tractable distribution to your vector. So you could just fit a Gaussian if it's a real value. Kind of harder to deal with correlations when it's discrete. So you might start off with just a fully factored distribution, so model each of the marginals independently. And then you'll immediately realize that there's limitations with that. And so you go down this hierarchy of more and more complicated models that become more and more computationally intensive. So the obvious thing to do after you've got simple distributions is to go to a mixture of those distributions. And the mixture model is just a special case of a whole family of more complicated graphical models that you could imagine building. So more complicated structure into that joint distribution. And then from your talk yesterday, I imagine that at the very, very bottom of the list for a lot of people in this room is some neural network that has 1 million parameters in it. That might be the very last thing that you'd consider. For some people here, I think that's going to be the last resort. So this talk is going to be about this last step. It's like, is this a completely insane thing to do? I've got a binary vector that's hundreds of 100 dimensional or more, which could correspond to an image. Is modeling that density using a very, very complicated model actually worth it? Do we actually gain anything over just the more obvious simple alternatives?
So 1 million is 100 squared?
Well, it's 1,000 squared the last time I looked, but yeah.
I guess I should have said where do 1 million?
Yeah, so it's often that you have, you might have some sort of quadratic interaction within the network. So we'll see some specific examples later and we can do the parameter counting. But there are people in Toronto who have models that literally have 1 million parameters in them, and they kind of do useful things. It's kind of spooky. Okay, so then how are we going to evaluate this list? There's a whole load of different ways you could evaluate a model, and I don't think any one item on this list is actually the whole story. I think they're all important. So something that's really good to embarrass people who've got a generative model is to ask them to generate samples from it, because those samples are just almost always going to be complete junk, and it just reveals the problem. So, for example, if you get some fancy probabilistic model that people use in computer vision, and they might be using it for some task like segmenting an image or identifying objects, if you ask them to actually draw a sample image from the distribution that their model implies, it will often look nothing like an image in their training set. You know, it could just be basically noise with some structure in it, which is just enough to capture the things they need to solve their task. Or if you get a model of text that people use in text compression or in some task, and you generate sample text, unless you're wanting to generate Lewis Carroll, it will look like junk. It's not, you know, it's not a perfect distribution. So I think generating fantasies is often kind of revealing of a model, but it's hard to make a quantitative assessment. If you've got two different models and you look at their fantasies, then it's going to be very subjective which of those you prefer, and you might want other measures. So something I dedicated a whole chapter in my thesis to was just computing one single number that you could ask of a generative model. You wrote down a model before you looked at the data, and then after you've seen the data, you can just say, well, how probable was the data under that model? And that's some measure of how good it is. So that's the marginal likelihood or the evidence for the model. That's usually an exceedingly hard quantity to work out. So if your model has millions of parameters and you're a Bayesian, you would have to integrate over all possible settings of those parameters to compute this quantity. So for the moment, I'm just going to assume that that's off, and we can't do that. Something else we could, yeah?
Just for clarification, are you sort of flagging up that there's a tension between the sort of robustness and vagueness of generative models and sort of highly informative priors, or are you kind of taking a stand and saying one of these is somehow better than the other?
I am intending to bring up that issue, and I'm not intending to take a stand necessarily, because I think the answer to that question depends on who you are and what you're doing. So, you know, I think there are some settings where philosophically this is a really nice thing to do. It's just very hard, and for today that's not going to be possible. So something else you could do is you could get your millions of parameters and just fit them. So you could come up with, if this is your parameter vector, you could just fit some particular estimate of what those parameters are. And then you begin to be a bit worried about assessing the model on the training data because you've fitted parameters to it. So we're going to look at some held out data and just say, well, how well does the model predict new data given what I fitted to the previous data? So this is like something that you can actually do a lot more often. And this will give you a single number that says how well you are at predicting things. So this is what this talk is mainly going to be about. And you'd have thought that it's really hard to do well on this measure. If you fitted 1 million parameters, surely you're going to overfit and you're not going to make very good predictions, but we'll see. Okay, so, but there's a whole list of more things we could use to compare. Yesterday there was a mention that maybe you just care about the particular task. Do we really care if we can model the density of all of our variables if all we care about is classifying some binary decision? So we could look at that directly. And then a final thing is that people might want to gain insight from their modeling. So particularly from the statistical point of view rather than the machine learning point of view, often the whole point of modeling is to gain insight into our data. So we're not just interested in like some scalar, oh, I managed to predict this okay. We want to know why it predicted it and what things that the model thought were interesting within the data set. Sorry, just a minute. Okay.
This only happens when David Mackay's in the audience.
Okay.
So far.
So, I've got a couple examples of these different ways of assessing things. So, something that's been quite hot in the last few years in machine learning has been this idea of topic modeling. It's a generative model of text, and something you do is you say the underlying cause of the document is that the document has some set of topics which it's going to talk about, and each of those topics has a distribution over the words that are going to be included in the document. Now, in terms of predictive density on a held out document, those models aren't really any better than the state of the art in text compression. So if you were going to do your comparison just on the basis of probabilities, there doesn't look as though there's very much in it. So these papers don't tend to quote that number. Instead, what they'll do is they'll create pretty pictures, and they'll say, this is what our model is showing us, and this is why it's an interesting model. So in this example, the model has learnt that there are hundreds of topics, and it's just showing 3 of them, and the distributions over the words in those topics. And the word play, or plays, appears in all of these topics, but one of the topics is about sport, and one of them is about literature, and Shakespeare and things, and the other one is about music. And so then it's sort of interesting that in some sense the model understands documents, because when it sees the word play, it assigns it the correct topic depending on what the document is about. So that's the sort of thing that's quite hard to capture quantitatively, I think. And then I've got an example of drawing samples from a distribution. This is a recent paper on building a model of natural patches from photographs and natural images. And again, if you do image compression, it's often quite hard to gain in terms of probability over just a simple model that says that images are locally smooth and they have edges in them. But looking at samples from the images, except on this screen, perhaps it's very hard to see, you can really pull out differences between models. So these are real grayscale tiny patches from photos. And then in this paper, they were comparing 2 models, and they didn't attempt to quantitatively say which model was better. They just said, well, if you generate images, they did other comparisons, but this was one of them. If you generate images from one of the models and you generate them from the other, then these have structure that's much more similar to this. And they're really asking people to eyeball the images. And
Both generative models were trained on the set on the right.
yes, and it was a much bigger set. That's just a subset. So both of those models had a very large number of parameters, but when you've got a high-dimensional object, often underfitting is the problem. So the thing on the left just hasn't managed to capture the larger scale structure that's there. Okay. So what I'm going to do is focus on one particular class of models that has been quite hard to assess, and it's quite a hot topic in machine learning, but quite controversial in terms of how worth it these models actually are. And I'm going to be using the term restricted Boltzmann machine throughout the talk, because that's the most accurate and specific term for the model I'm going to be describing. But if you haven't heard of restricted Boltzmann machines, you may well have already heard of this model, because it's a special case of models that you probably have heard of. So if you know what I mean by Markov random field, Ising model, or exponential family model, then this is a special case of all of those classes of models. And here's a very small one to explain what's going on. So this is a latent variable model. We've got some data, which is a vector v. So that's our visible observed quantity. And the model says that underlying the observed data, there were some hidden variables h, which somehow caused the observation, or were related to the observation, but we didn't see them. So the model specifies a joint distribution over both quantities, the observed quantity and the hidden quantity, and it then expresses some distribution. And here is what would happen if you just had one hidden variable and 2 visible variables. Now, for illustration, I've made the visibles real, although later in the talk, everything's going to be binary 0, 1. So here is, along this axis is visible 1, and along this axis is visible 2, and I've got a grayscale indication of the probability distribution. So through interactions with this hidden variable, there's this soft linear constraint that says the region at the bottom of the image is more probable. So you're more likely to have a joint setting of B1 and B2 down here than up here. So that's the thing that a single latent variable can do in this distribution. It's just able to enforce some linear constraint if the hidden unit is turned on, if the hidden variable is set to 1. And if you had a different model that only had one latent variable, then you could set the parameters differently and come up with a different linear constraint. So if you've only got a single latent variable, there's not very much you can do in these models. What's interesting is what happens when you combine having more than one latent variable. So this is a graphical model for a restricted Boltzmann machine with two hidden units, and the joint distribution is actually the product of the two joint distributions that I showed you before on the left. And if you had a mixture model that said sometimes you generate densities like this and sometimes you generate densities like this, then you would just get the sort of the linear combination of these two plots, and you would have density all along the bottom and all along the top. When you multiply the densities together, you get something different, and these two hidden units now sort of have to agree on what's a good place to be. So the resulting density has probability sort of at the intersection of where those two latent variables like to be data.
Are you using latent variables for those, like the hidden layers in a neural net?
Yeah.
I mean, we also think of it in terms of factor analysis.
Okay.
But, I mean, I think there's some equivalency in the sense of if you think of latent variables as a lower dimensional space.
Yes. So, I mean, this is a type of neural network. It's a stochastic neural network, so the hidden units are random quantities that can be 0 or 1. You also get deterministic neural networks where the other variables are like a deterministic function of the inputs. But yes, it's sort of like a nonlinear factor analysis.
Maybe it's a good idea to say how it's not like factor analysis as well, because you don't have any arrows.
Okay. So in factor analysis, you've got these sources which are a priori independent. So the generative model is you generate the sources independently, and then you generate data. And in that graphical model, as David said, there are arrows which capture that sort of notion that these units are independent because they're not connected. When you drop the arrows and you make it an undirected model, the conditional independencies are different. So now these variables are actually a priori correlated, because in this distribution, we know that we tend to be down here, and being down here corresponds to both of these being turned on, so they're correlated. But when we observe both of these quantities, that kills all of the connections, and these are now independent. So given an observation, the hiddens are all independent, which is different from a directed model. Okay, so here's another example of how you could combine two hidden units into a distribution with two latent variables. Here there are constraints which are sort of contradictory. So the first hidden unit says, I like to have density down here, and the second density says, I don't like to have density down here, I like to have it up here. But you've got to have density somewhere in the result. So it's not always that the resulting density has to have agreement from every single latent variable in the model, because the h's can turn to 0 and kill this term. So some of the experts or latent variables in this model can just turn off, and then the resulting density will be that you'll either respect one of them or the other, or sometimes neither. So.
But by your graphics, because for me the total area under a density should be 1. Somehow the total grain is.
Yeah, it's kind of, yeah, I haven't done the thresholding very well. If you want to tell me how to do that afterwards, that would be great, because yeah, I appreciated that wasn't very good. Okay, so those were just like toy examples to give you some idea of what sort of things these models can capture, but the way these models are used is actually much harder to see what's going on because they're big. So this already looks kind of big, but this is a tiny one because there are only about 20 variables and 20 hidden variables. In applications, you can literally have hundreds of variables or maybe 1,000, and that corresponds to then hundreds of thousands of parameters or millions of parameters, because for every observed quantity, there's a connection to every latent variable, and so there's this quadratic number of parameters in this.
So it's hidden variables at the top and
Yes.
view variables at the bottom.
Right. So I think it's easy to be skeptical about how how sensible it is to just write down this sort of thing and run with it, because as soon as you've got this enormous model and a very large number of parameters, for me it's very hard to see what's going on, and it's a very difficult fitting problem when you want to fit all these parameters, and so you might get a different answer every time you refit to data and try different optimization algorithms. But I think there's some reason to treat this sort of neural network seriously, because they've been enormously successful in a few applications. So very recently, people in Toronto used this model as just one of the things they did entering this competition, which was run by Netflix. So there was an enormous data set of movie ratings from, I think there were millions of entries in this big sparse matrix, and there's a prediction challenge to try and predict what users of Netflix will want to see. And the Toronto team hasn't won this competition. They did reasonably well, but the winning team did read their paper, implement their method, and reported the difference that using RBMs in their mix of methods provided. And because these types of models did something different from every other collaborative filtering method they used, they got a performance increase. So it's a massive real-world application, and something interesting is going on. People are also using these for dimensionality reduction, as you mentioned. So if you have a very small number of hidden variables compared to the number of visible variables, then you get some compact representation of any given input variable, because you can look at what the hidden variables should be, or the distribution over the hidden variables for any visible vector, and that's something that you can then use as sort of a feature that you can extract from your complicated object. So there are a lot of applications where step one is do this crazy thing, step two is extract some hidden representation, and then use whatever algorithm you like on top of that, and that might work better than just running your favorite algorithm directly on this very large high-dimensional visible vector. So I touched on this already. The graph has a structure, partly because it's undirected and partly because it's bipartite. None of the visible variables are connected to each other, and none of the hidden variables are connected to each other, which means that we can write down two conditional distributions immediately. It's very tractable to compute what the conditional distribution over all of the hidden variables is given the visibles, and vice versa. And this distribution is fully factored. So for any given input, image, or binary vector, we have a compact representation of what all of the hidden variables are. And that's why we can then immediately use it as a feature vector in some other algorithm. Whereas if we had a directed graphical model or some other latent variable model, it would be difficult to capture what the hidden variables are or what the distribution over them is for the visible vector, and it would be hard to use the model immediately for anything else. The other thing that we can do, given that we know both of these conditionals, is that we can do Gibbs sampling. So we can run a Markov chain over our model. So I'm sure you all know about Markov chain Monte Carlo, but my weird notation that I'll use is that if you've got a setting of a variable at time t-1, you draw from a distribution t where it's going to be at the next time step. So you evolve this Markov chain over variables in your model, and that's a way of sampling from the distribution you're interested in. So these two conditional quantities, we can just iterate between these. Given the visibles, we can sample the hiddens. Given the hiddens, we can sample the visibles. We go back and forth, and we take a random walk over the data space and the hidden vector space at the same time, in fact. So now we can immediately do some of the, we can immediately try to assess the model in a variety of ways. So I've said how you can extract hidden variables, and so you can then put it into an application, and you can judge how well you're doing on that application. And now we can also draw samples from the distribution, at least correlated samples, and so we can look at fantasies and see how good they are. So for a long time, that's what people did. The papers had pictures of fantasy drawers, and they'll say, we got a 1.3% error rate on this classification task, as opposed to 1.4%. But I think it would still be nice to say, well, what's P of V? So we've trained this model. If I just used a mixture of Bernoullis, is this actually better, like in terms of a density estimate? So let's look at how you compute P of V. So we've got this joint distribution over visibles and hiddens, and so we just want to marginalize out the hiddens. But this is an exponentially large sum. So if we have 500 binary hidden variables, it's a sum over 2 to the 500 things. And if we substitute in our expression for this joint distribution, we can actually do this sum because it decomposes for any particular v. So the distribution was 1 over z, the normalizer of e to the sum energy term that said how compatible settings of the visibles were with settings of the hiddens. And because this is contains a linear sum, this thing we can actually do very easily in one line of MATLAB, and it's very quick. What we don't know is what this normalizing constant is. So up to a constant, we do know what the probability of any test vector is. And if we have two different putative images or visible vectors, we can say which one is better and by how much. But we still can't answer this question of, is this better than just the dumb obvious thing you might have done instead? Because that will all come down to what this constant actually is. So if we want to evaluate these models, we have to evaluate the normalizing constant. And this normalizing constant is an exponentially huge sum that doesn't decompose in any clever way. There's no shortcut here. It's sort of provably hard to solve exactly in the general case. So let's think about why this sum is hard and why it's difficult to approximate. So for any given setting of V and H, this is just some quantity that we can evaluate. It's just as an awful lot of settings of V and H. And we might imagine that perhaps if we just looked at a few settings, we could come up with some Monte Carlo average, because if we just sort of get a feel for what a typical term in the sum is, we know how many terms there are in the sum, so perhaps we can make some progress that way. But that's kind of hard. So if we have 28 by 28 binary images, which are, that's the size of the MNIST digit data set that we're going to see later, then I estimate that the fraction of those images that actually look anything like digits is about e to the minus 400 and something. By the end of the talk, you'll know where I got that estimate from. But
Are you going to tell us what it looks like as well? Well, we have an intuitive idea, but you're obviously counting. So.
That have it might be slightly circular, because I'm using an idea of how, from my experience, how probable I think a digit is under a very good model. So if under the best model I've ever seen of digits, the probability of a digit is e to the minus 80, then that gives me some idea of how many digits there must be, because their probabilities must sum up to 1. So that's what I'm doing. But it could be that I just haven't seen a much better model than that. But you can come up with some reasonable idea of like the maximum probability that you can possibly have. I mean, for a start, we've seen 60,000 of these, and none of them are the same. You can start you can start to see that there must be a lot of them. Okay, so just uniformly picking some random setting of V and H is going to be futile, because we're not going to see any of the terms that actually have reasonable probability, because they live in some tiny, tiny, tiny subspace of the space of all images. If we're just interested in big terms that actually look like digits, the ones that are really summing up to this total probability mass, then we'd imagine that perhaps we could use the samples that we got from our Markov chain Monte Carlo, because that was an algorithm that explored the things that look like digits. So it's not actually obvious how to turn those samples into an estimate of the probability. So the annoying thing about Markov chain Monte Carlo is it doesn't need the normalizing constant of a distribution, but it doesn't necessarily tell you what it is either. And there are several methods that attempt to turn MCMC samples into an estimate of this normalizing constant, but none of them work in this problem, and perhaps I'll discuss that with anyone afterwards if they want. So the obvious Monte Carlo approaches don't really work. And the other thing we could try and do is come up with some deterministic bound. So there's a massive family of variational methods that will both upper and lower bound this quantity. And perhaps if we could get those bounds to be close, then we'd have some reasonable idea of where it is. Now, I can't claim that I've tried every single bound out there, but we're really interested in upper bounds because, I'll just write this so that we remember what we're doing. So the idea is that there's some unnormalized quantity that we can evaluate easily, and we're trying to evaluate the normalizing constant, and then that's the thing we want. So if we underestimate the normalizing constant, we'll overestimate the test probability. So if I'm in the business of trying to convince someone to use a model, and I say, well, I think that this model is 100 times better than a mixture of multivariate Bernoullis, but it could be arbitrarily worse than that, I don't know. That wouldn't be a very useful statement. So the way to get a statement that says the model's at least as good as this, and that's better than what you're currently using, is to get an upper bound of the normalizing constant. But all of the upper bounds I've tried are loose by hundreds of nats. So a nat is like a bit, but log 2 different. It's a natural unit of information. So that means that the true answer is just e to the hundreds in terms of probability away from what the bound is telling me. So it's just completely useless when the difference between models might only be tens of nats. So it seems that all we can do is just invest a lot of effort into the most state-of-the-art normalizing constant algorithm that we can find. And that isn't going to be anything simple, unfortunately. But there is a whole literature on very advanced Monte Carlo methods that will estimate normalizing constants. And I could give a whole talk just on those, but instead I'm going to just describe one and assert that it's one of the better ones. So this family of advanced algorithms, they tend to have the following flavor. Instead of just sampling from one distribution, like the uniform distribution over picking V's and H's at random, or the posterior distribution fitted to data, instead you look at a whole family of distributions. So if we've got the joint distribution for our fitted parameters, we can consider softening that by raising it to some power between 0 and 1 for a whole range of values of beta, which physicists will call an inverse temperature. And then the idea is that we can interpolate between something very simple like the uniform distribution over all binary vectors, or if it was continuous, some base Gaussian distribution that we fitted, and our final complicated model, which is presumably very spiky. So the cartoon is that in a continuous space, we'd smoothly move between our simple base distribution, which here is pi, and our final distribution. And in terms of a model of digits, these are samples from a base background distribution, which isn't actually the uniform distribution. This is every pixel has been fitted to its marginal distribution. So each one of these squares is a separate sample. So there are 16 generated samples from this model here. And this is the final fitted model. So these are 16 fantasy generated digits generated from the model. And then there are these intermediates, which sort of are somewhere between noise and looking like digits.
So those are independently
generated? Well, they're from a Markov chain, but it's been run for a long time, and there's a big gap in between each image. So it's not actually possible to generate IID samples from these distributions because there's no tractable way of doing that.
Can't do random restarts or something?
You can, but there's no guarantee that that actually helps. I mean, whenever you start somewhere, you've introduced a bias, and it's difficult to prove you've got rid of that bias. That's a difference from directed models, because generating from a directed model is trivial. You just generate all of the latent variables independently and then sweep down the graph. So why are we doing this crazy thing? To some physicists, it will be an obvious thing to do because they have systems where they have to estimate things that correspond to this normalizing constant, and there's a physical analogy that involves cooling down a system from very hot, where everything's scattering about, to very cold, and they call this thermodynamic integration. But in terms of what we're doing, we can just look at this as some math that works. So we're interested in the normalizing constant of this distribution. And if this distribution is very simple, then we'll know its normalizing constant, because if it's tractable, then we can just compute it analytically. So a very simple identity is just that the ratio of those two normalizing constants, the one we want and the one we can actually compute, is equal to some product where almost all of the terms cancel. So that cancels, that cancels, that cancels, that cancels. So this is an identity. And each term in this identity is the relative normalizing constant between two adjacent distributions. So I estimate the normalizing constant ratio between these two, between these two, and between these two, and then I can combine all of those estimates. Now, when two distributions are very similar, it's much easier to work out the relative normalizing constant, because now you can sample from one of them and compare what the ratio of probabilities is like in the other one that you didn't sample from. And that's simple importance sampling is what it's called, and it works when the distributions are very similar. Okay, so here's more technically what's going on. You construct some very big joint distribution over the whole sequence of digits that you're going to see. So if you combine this image, this image, this image, and this image, this is like an annealing run where you started off at high temperature and you followed a Markov chain and you gradually cooled it. If you concatenate all those things together, that whole run that you saw, and call that big V, then you can construct a distribution over that big V. And you can construct two distributions. One is the one that you actually did, the algorithm you run, which I'm going to call Q. So we proposed a setting of the big V by starting at the hot temperature and cooling. And then we can compare that to a distribution where we first generated the final digit from the distribution of interest. So we can pretend that we generated this from our model, which is something we can't do directly, and we went backwards. So that distribution I'm going to call P, this backwards distribution. And now these two massive distributions are very similar, because each individual step of heating and cooling didn't do very much if I have many intermediate temperatures. So now I've got two distributions that are very similar, and I can do importance sampling. So this is really just a technical trick that, yeah.
Sorry, I'm just feeling a bit confused. You've got a V0 on the right. Is that the one that corresponds to drawing from the simple model? Because you used to go, the simple model was on the left on the previous slide. I'm wondering, have I switched things around?
No, I've switched things around, yes. So the progression here is reversed because I've taken the figure from something else. Yeah, sorry.
So importance sampling starts at the right.
Yeah.
V0, and you cool things down, as it were.
Yeah. Okay.
All right, and you're saying the real distribution is you start at the nasty model and you warm it up.
Yeah.
That's called P.
Yeah. So the idea is that once you've constructed these very large distributions that involve an entire annealing run, you can then just do naive importance sampling on that even bigger object. So again, I think this is a surprising thing that it works at all, because importance sampling doesn't work in high dimensions. It's a terrible algorithm for high dimensional problems. And here we've made the problem even more high dimensional because we got our original high dimensional problem that was a binary vector of length 700, and then we concatenated together 1,000 of those for 1,000 different temperatures. And now we have a 100,000 dimensional vector, which we have drawn some setting of by doing this annealing procedure. And then we compare that probability over a 100,000 dimensional vector to some other distribution and do importance sampling. And amazingly, that works because it's been very carefully constructed so that those two distributions we're comparing are very close. So, I imagine that's not entirely clear, but I'm here for a few weeks, so you can talk to me. Let's see what actually happens. So, if you very carefully construct a special case of one of these models, you can work out the true normalizing constant. That isn't normally true, but here's a toy example where it is. So this is a really expensive procedure. In order to make these massive distributions very similar, you have to have an awful lot of intermediate steps so that every pair of adjacent distributions looks the same. So here's the true answer, and it's sensible to look at the normalizing constant on a log scale because it's just some positive quantity and it tends to be very large. And in order to get like a reasonable answer, a typical thing for the models of the size we're interested in is it's going to take hours to work out this constant to reasonable error bars and to get the right answer. And that's not necessarily unreasonable because this is something we only have to do once to evaluate the model. So once we've got this single constant, we can then apply it to any test vector. So if we've got a test set of 10,000 images, we compute this constant once and then we're done and we can just evaluate this cheap function for every test vector. And if we've spent a long time trying out different models and it's an expensive data set, maybe 5 hours isn't so long, but you know, it's kind of expensive compared to a lot of simple statistical techniques.
What are the error bars reflecting that?
So it's a Monte Carlo method, and for every run of this procedure, we get some estimate, and then you run the procedure many times, and you construct empirical error bars from that are kind of dodgy because they're only asymptotically correct. And it could be that...
Is it a quantile?
I think this is... The estimator is unbiased in Z, so you can just look at the empirical variance in Z, and then you put it through the nonlinearity of log Z, which is why the error bars aren't symmetric. But it could be that if you'd run the algorithm for a bit longer, you'd have got some enormous weight that would kick your estimator off and your empirical variance just hadn't reached the asymptotics yet. So if there's time, I might come back to that. But okay, so here's finally one of these comparisons I've been promising. So one of these two models is a mixture of multivariate Bernoullis, samples generated from a mixture of multivariate Bernoullis. They've seen the same training data, and they've got similar numbers of parameters, because a mixture of multivariate Bernoullis still has a lot of parameters if you've got a large number of mixture components. And one of them is samples generated from one of these restricted Boltzmann machines. And the restricted Boltzmann machine is about 40 nats per digit better. So that means if you were going to use these models for compression, the run length, the encoding would be 40 nats smaller. So the question is, which of these is which? Which is the samples in the multivariate Bernoulli? And David will know. So
I'm not actually understanding this setup here. You've told us quite a lot of different models. There's real data, and then there's the model you're trying to evaluate Z for, and then there's the second model you introduced to help you evaluate Z, and now you're telling us two more models, and I'm lost.
Okay.
Which of these is the thing that used to be called P?
Okay. So
and where's the data come from?
we've got a big training set of digits, which has 60,000 digits in it, and we trained a mixture of multivariate Bernoullis using EM on that data set, and then we generated samples from that model, and that created one of these two pictures. That's one of the pictures.
Okay, so you make a so you fitted a model that's a mixture of 10 or 20.
100, but yeah.
100 Bernoullis. So that's great for sort of doing templates of what 100 different digits look like.
And the other image is a restricted Boltzmann machine, which used a very complicated training procedure I'm not going to go into, that one of the grad students in Toronto, created a weight matrix and gave me the MATLAB file that contained it. And then we did this complicated annealing schedule to work out Z. And then for a test set of size 10,000, we evaluated this for every test vector. We took the log and then we averaged. So we did that and we said, oh, it's much better than the mixture multivariate Bernoullis. And then using MCMC, we generated samples from that restricted Boltzmann machine and generated the other image. So now the question is, which image is the really good restricted Boltzmann machine and which image is the mixture of multivariate Bernoullis? Does anyone want to guess? Mike? Okay. So the really, really good model that's 40 nats better, which means that each digit looks e to the 40 times more probable, is this one. Okay. And this is the really dumb model that's much worse, according to the numbers. So what's going on? So we've got some high-dimensional data space, which I'm going to draw in 1D. And we've got this very fancy model, which has caught into all of the details of digits and picked out this tiny space that's got digits. And that's why it does well at encoding. And then, due to reasons of the way it's trained, it also just has some massive spike somewhere else. And this spike actually contains most of the probability mass, like 95% of the probability mass. So what's going on is I showed you pictures of where these models sort of cut off planes of regions which are good, and then the intersection of those regions is where the density is. And that's kind of a hard thing to control. So the training procedure will carve out linear regions sort of that finds the manifold of where digits lie, and just spuriously some other bit of this massive space might have high probability mass, and the training procedure didn't find that and squash it down. So now, this region is much, much better modeled than the mixture of multivariate Bernoullis. As David said, the mixture of multivariate Bernoullis basically has very dumb templates around the digits, and then it doesn't really know anything about spatial structure, so they all look very noisy because once you've picked your template, you generate the pixels independently. So this does badly on logprob, whereas this one wins. And the reason all these samples look terrible is that they're all in this spike that has nothing to do with digits. But in terms of logprob, you just have to pay enough bits or nats to say that you're in this region, which might only be log 10 if this is 90% of the mass. And then once you've paid that fixed cost, you're done. So in terms of log probability, this isn't penalized, even though all of the fantasies are terrible. And if you just looked at these, you wouldn't say that that's a good model.
I guess for me, I have trouble with this because you never told us what you mean by looks like digits. And I could imagine some definitions of that under which these look better than those. Could that be going on here?
Yeah, so I'm just thinking very intuitively. I'm just guessing, although I haven't done any psychophysics on this, that most people would think these look more like digits. But it's open to interpretation, and there are certainly ways in which this model is much worse, and there are certainly ways in which it's much better. And how much cost you assign to those depend on what you want the model for. I'm just trying to sort of highlight that there are many aspects to this sort of model comparison, and that it's not necessarily obvious. Okay. And so you don't go away with thinking that these restricted Boltzmann machines are really junk. The graduate student went away and worked harder and improved his optimization procedures. So this is the sort of thing it can do. These are examples drawn from the training set where it's been binarized. So you can see what it's learning from actually look pretty crappy. And these are samples from a model that was fitted, and it takes like 8 hours to fit one of these things or something, and then 5 hours to evaluate it. And you probably have to look at more of them to know if it was doing a really good job, but I feel that it's getting fairly close. And so these images are 750-ish pixels, which is about 550-ish nats if you just encoded each pixel as a binary coin flip, and this model is compressing them down into less than 90 nats. Okay, so I do actually I've got more material, but time's pressing on, so perhaps I'll just ask at this point if there's questions rather than marching on with a load of stuff that's completely different.
The actual estimation of the parameters must be terribly challenging.
Yeah, so that's another whole talk. So what they're wanting to do is maximum likelihood, but you can't actually evaluate the likelihood because, I mean, what we're trying to do here is evaluate P of V. So it seems that it should be an impossible task, but the gradients of the likelihood are a more reasonable thing to estimate than the likelihood itself. So they're able to do something that looks a bit like stochastic gradient descent or ascent on the likelihood by sampling. So they're able to get sample-based estimates using Markov chain Monte Carlo of the gradient. And that's what they do, but then there's a lot of detail in exactly how they do that, which is the difference between this and that.
Do they produce reliable estimates in any sense?
No.
Haven't shown that they're reliable, but they might be reliable.
There are some asymptotic results that I don't really hold by because they're not very interesting. So there are some algorithms for which you can say that eventually you'll get the maximum likelihood answer, but I think it's pretty clear that they're nowhere near being in that regime because the details of their training procedure make a big difference on the type of model they get at the end. And several of the training procedures sort of should all be doing the same thing asymptotically, and they don't do the same thing. So I don't really believe any of the results on proving that the training procedure will work. So, but it's a big area of research where they're trying out all these different things, and so it seems very important that they have a very solid way of comparing the training procedures, and getting as many handles on that as they can seems important rather than just some particular classification task which might ignore big details of the models. Should I go on or should I stop there?
I have a question too. In neural nets, often some of the hidden nodes do completely nonsensical things. I don't know whether some of your latent variables, whether there's a way to check for it.
Right. So I don't have a plot here that will show you this, but I can just describe. So if you look at the parameters associated with any particular latent variable, they're connected to every single visible variable. So in this application, they're connected to every pixel in the output image. And so then you can just plot a picture of what they're doing, and you could call that a receptive field if that's jargon you're happy with. So the mixture of multivariate Bernoullis, any particular component just says, have this particular template that looks like a digit and add noise. And the restricted Boltzmann machine, because it combines several of these constraints, can focus on something much more local. So the parameters might say, in some tiny region, I want a little bit of stroke here, or not, I could just be turned off and that doesn't happen. And in the rest of the region, I don't care, I just make uniform predictions, which then other latent variables will have things to say about. So when you look at the latents associated with an image, there'll be lots of them turned on, and they will be constructing little local bits of the digit and collaborating together to build up the whole thing. Most of the time, most of the latent variables will be 0 and contribute nothing. And it could well be that the training procedure doesn't find anything useful for some of them to do. So they might be junk, but then their parameter might also be that they're turned off most of the time and they just get pruned out. If if I did the next bit, it would probably take 10-15 minutes, so I think I should just leave it there. Okay.
We don't have another offer for short PS from anyone. We've got something for 10 minutes.
Okay. Right. So I've only talked about one style of model that has this particular simple property that all of the hiddens are independent given the visibles, and that makes things particularly simple. You can do some things immediately. I think probably very few people in this room have ever used the model that has that property, and it's much more common for all of your latent variables to be correlated, so you don't know which of them are responsible for your image, and there might be some negative correlations and explaining away type effect. So basically any other model you'll come up with has the property that the latents are correlated. A directed graphical model or Bayes-net, all of the latents, while they're independent in the generative process, conditioned on data, they're correlated, and other types of neural network where there's more than one layer of units or the units are explicitly connected will all have correlations. And so now the sum before that over hiddens that I said you could just do analytically, you can't do anymore. And we need ways of dealing with that as well. So to get P of V, we might need to estimate a normalizing constant to know this joint probability, but we also need to then, on the outside, sum over all settings of the hidden variables. And that turns out to be a much easier problem in a lot of cases. And often, depending on how the model has been fitted, that distribution over hiddens is relatively simple, or at least you might want it to be. You might deliberately fit models where the distribution over hiddens is simple because you want a neat interpretation of the data so that it can be fed into other methods, or so that it actually makes sense when you look at what the hidden units are doing or whatever. So P of V is itself a normalizing constant because it's the normalizing constant in Bayes' rule. And there's a trivial identity where you just swap these two things around, where you say P of V is equal to this for any setting you like of the hidden variables. So if you just have some heuristic for finding a point estimate of what the hidden variables are likely to be for a given data vector, you can just set that particular setting and then look at this ratio, and that's the value of your probability. So if this joint probability is tractable, which for Bayesian networks it is, and otherwise you can get it by estimating the normalizing constant using the first half of the talk, then all you need to know is this probability. So the probability of your particular special state given your observation. And this distribution, which before was fully factored, is often not too complicated. And now the problem with bounds is swapped. So if we overestimate this probability, then we'll underestimate this and we'll be in some sense conservative. So I'm kind of happy with just coming up with any crappy estimate of this I like, as long as it's going to be an overestimate of anything. If there's a horrible failure made of my algorithm, it's an overestimate. At least then I'm making a conservative claim if I'm in the game of trying to compare to simpler alternatives. So there's a method of estimating normalizing constants which usually isn't very good, but in this setting turns out to be kind of actually works very well. So I'll write up this identity just so I don't mind. So this is just to remind us that this is the quantity we want and this is the reason. Now, this is the posterior distribution over the latents given the visibles. We can construct a Markov chain over that thing if we can't sample from it directly. So if we run a Markov chain to sample from that distribution, it better have the property that if we were to draw a hidden vector from the distribution we want, this posterior distribution, and then evolve it through one step of our Markov chain, the distribution over where we end up should also be the correct distribution, the posterior, given the visibles. This is like the basic consistency that all Markov chain algorithms obey. Now, given that, there's a simple estimator of this term, which is just a sample average of this big sum. So you draw samples from this distribution and you average this term. So that's all this is saying. You draw S samples from the posterior using Markov chain Monte Carlo, and you average this transition. Now, asymptotically, if you ran your Markov chain for a long time, that would be an unbiased estimator of the quantity you want. Now, this is the quantity we want, and if we're unbiased in this, then unfortunately by Jensen's inequality, we're not only not unbiased in 1 over that quantity, but the shift, the bias that we create means that we're likely to overestimate P of V. So this is what we want. This is the expectation of our estimator, and when we get the expectation of the whole thing, we're actually going to compute the bounders the wrong way. So if we ran our Markov chain for a very long time, so we had independent samples, we would actually not be doing quite the right thing. We're likely to be biased in a subtle way. So it'd be nice if we could somehow bias this procedure in just the right way to fix it up. And amazingly, there's a way of doing that. So the intuition is we want to overestimate this thing, if anything. And we're running a Markov chain that explores the latent space. So the way to overestimate this would just be to start there. So if we start in the region that's near the state we're trying to estimate the probability of, we're going to be wandering around it and it's going to look more probable. That's the intuition. It's a bit more complicated than that, but there is a procedure where you start at the special state, you generate a random number of Markov chain steps starting from there, you generate a second Markov chain also starting from there for technical reasons, and then based on that, there is an estimator which is based on importance sampling, which means that we end up getting an unbiased estimate in P of V. So it's a similar idea to in ill-importance sampling in that what we're doing is we're generating a big joint distribution over more quantities than we started with, and it has the property that it ends up working better than the dumb importance sampling. So if I just generated one sample if I just took one Markov chain step starting at my special state, I would only explore a tiny amount of the distribution, and it would actually be a terrible importance sampler because my distribution I'm sampling from would be very compact. And when you draw from a very compact distribution into importance sampling, that tends to be a very bad idea. But by taking many Markov chain steps, we're able to improve the quality of our importance sampler and get better results. So this is something I'm still working on, but actually it seems to be working very well and works much better than the obvious variational alternatives. So yeah, I don't want to go on for too long, so I'll stop there. So perhaps I think it would probably take 10-15 minutes to explain this properly, but the idea is that there's this sort of very simple Monte Carlo technique which for this particular problem of latent variables is working very well.
What is T tilde and all that?
Yeah, so that's part of the technical conditions of the algorithm to just make it work out. So for any Markov chain operator that you might write down, there's a corresponding what's called a reverse operator. And if your chain satisfies detail balance, those two things are actually the same thing. So I'm just being pedantic that if you have non-reversible Markov chains, then you have to be a bit careful about constructing the way you come up with your estimator. But it's detailed, it's not important. Because in practice, it doesn't actually matter. Like when you look at the results you get, it's all much the same. But the proofs only go through if you use the reverse operator in the way in the graph. Okay.
2 o'clock, Steve Marino gives a session for those interested. about trees.
Yeah, it's really a discussion between Patrick and I, and everybody's what we're doing.
A little bit.
You don't have to put